Okay, I'm going to do an example of Gauss's law for a conducting sphere specifically. So first let's think about a conductor. So remember, a conductor means that the electrons are free to move. So let's imagine that we have a sphere, representing in 2D, and let's say we bring a charged rod next to it and charge it up. Okay, so we're going to give it some positive charge or take away some of its negative charges. More like what happens. Okay, when those charges move onto the metal, if I put another charge here or put a bunch of them in one spot, they're going to spread out, right? Because they're all repelling each other. So they're going to end up spreading out. They'll be always on the surface of the charge because that is where they can get the furthest away, right? If I put a plus charge here and a plus charge here, they're going to repel each other and want to move out. And so they'll end up on the surface. So all of the charge will be uniformly distributed around the surface. And again, this is just 2D, but this would be in 3D as well. Okay, so we need to understand that that's where the charge goes for a sphere, a conducting sphere. Okay, so now let's look at Gauss's law and see if we can figure out what the field is then inside the conducting sphere and outside of it. So what is our electric field inside and outside sphere? Okay, so this is different from a sphere that has a uniform charge density, right? This is specifically a conducting sphere. Okay, so let's say it has a, let's put that in here, with charge Q. So let's draw a nice circle here. And again, assume what's a positive charge, just to make, I don't know why, I like drawing pluses better than minuses, I guess. So we'll spread that out around the outside. And again, this is a sphere, I'm just drawing it in 2D, right? So there is a dimension here, and that will all be on the charges all on the outside. Okay, so first let's look for, let's define the radius, big R. And first let's look at when R is less than big R. Okay, and also let's draw a Gaussian surface. So if I want to know at some particular radial distance, what is my field here? Okay, so I'm going to draw my Gaussian surface is going to be a sphere, right? It matches the symmetry of my object. And again, we're just drawing a circle, but this is also a three-dimensional sphere inside of it. And then we can start with Gauss's law, right? That says if I integrate the electric field dotted into the area all around my closed surface, right? That's the closed surface integral. It will tell me it's equal to the enclosed charge over epsilon naught. Okay, and again, whenever we do, if we look at this field, right? At the surface, the field, the electric field is always going to be pointing out away, perpendicular to the surface, right? It's just radially outward. Okay, so we convinced ourselves to start out with that all the charge is outside on the surface of the sphere because that's where it will can be furthest away from all the other positive charges. So if that's true, that means that our enclosed charge is 0. Okay, and then I don't care what this integral is, but if usually we're picking it so the electric field comes out, and we're picking it so that our area vectors dA are always positive to the parallel to the electric field. So this dot product is becomes this, the integral of dA, right? Because E dot dA equals the magnitude of E, the magnitude of dA, and then the cosine of the angle between them. And when they're in the same direction, theta is 0, cosine of theta is 1. And then we're also picking it a shape so that the electric field is constant along that surface, so it comes outside of the interval. So we can kind of go through this side just for practice, right? If I integrated my surface area around this Gaussian sphere in here, I'm going to get 4 pi r squared. Right? We don't actually do the integral, we just think about what that surface area is. But regardless, it's equal to 0 on the left side, or on the right side. So that tells us the electric field is 0 when r is less than r, big R. Okay? So the electric field inside a conductor is 0. Okay, so that's an important result. This is relates to like a Faraday cage. I encourage you to Google that for Google the Boston Museum of Science Faraday cage. You'll see some cool videos. Okay, so what if instead of the sphere we had a spherical shell? So let's draw that again. So here is our nice circle. Put the sheet under, it's a little bumpy. Okay, and then let's say we have a thin shell. You guys, I forgot to finish the last one. Hold on. What if we were now at r greater than r? I forgot about that part. Okay, so we do the same application of Gauss's law, right? So, but now my Gaussian surface is going to be out here somewhere. Okay, so this will be my new radius that I'm talking about, right? Somewhere outside of the size of the sphere. So again, I do the electric flux, which is the integral of E dot dA around the closed surface, is enclosed charge over epsilon naught. So I did this side already, right? The same kind of thing. It's a sphere. The electric field is parallel to the area vectors, and so I get on this side E 4 pi r squared. And then my enclosed charge, once I get outside the sphere, my enclosed charge is the charge of the sphere. So it's going to be Q over epsilon naught. So when I solve for my electric field, I get my enclosed charge divided by 4 pi epsilon naught r squared. And we can really write this, it's really telling us the electric field as a function of radius, right? Because if I move my sphere out, the electric field is going to drop off. So this is really E as a function of R. Okay, and then remember as well that K is 1 over 4 pi epsilon naught. So that the electric field, when we're outside, R greater than the radius of the conducting sphere, it looks like KQ over R squared. So this is the same as a point charge. We saw this with a charged sphere, same thing. Once you get outside, it looks just like a point charge. Okay, it's exciting. Okay, so we've done both of those. So now let's go continue on to the conducting shell. And I guess we could make this one negative. So let's make it charged with a negative, an excess of electrons. Okay, so my electric field vectors are going to show you what a positive charge would do, right? A positive charge, the positive test charge is going to get drawn down to the sphere. Okay, so what is our, so this is a conducting shell. It's got a charge Q, let's say again, or charge minus Q, right? And a radius R. And we'll make it thin so it doesn't actually matter if we're pointing to the middle or the the inside or the outside. And let's say, again, we want to find the electric field for R less than R, and then the electric field for, well, once we're outside the charge sphere. All right, so let's do the inside first. So Gauss's law tells me that the electric flux through an enclosed surface is equal to the amount of charge enclosed divided by epsilon naught. Okay, so when we are inside, let's draw our Gaussian sphere. So we're talking about someplace in here, right? A radius less than big R. Okay, and again, it's a spherical surface. Okay, so let's go through our Gauss's law, right? So we're picking it such that the electric field and area vectors are parallel or anti-parallel in this case. And then we're also picking the surface so that based on the charge symmetry, the electric field should be constant, right? So our integral just becomes the electric field comes out, the dot product, they're parallel. So we'll worry about direction in a minute. So cosine of theta is 1, that comes out. And again, this integral of my little area vector around this entire Gaussian sphere is going to be 4 pi r squared. It's the surface area of the sphere. Okay, and that's going to equal Q enclosed over epsilon naught. But what is my charge enclosed inside of this sphere? Right, all the charges outside of there. So this again would be 0. Okay, so the electric field inside the charge cell is going to be 0. So you can kind of think about that, like what exactly is happening? Because it seems like how could it be 0, right? So, but let's say we have a little positive charge here, right? You think, oh, it's going to be drawn over here. It likes that negative charge, but there is a bunch of negative charges over here that are pulling it that way as well, and so that's going to actually the net force will cancel. So basically, when you sum up the forces from all of these charges, if we did the integration, you'd see that they are all going to cancel out. So it's kind of a cool thing. Okay, so then what if we're outside the sphere, R greater than R? So we start with Gauss's law. It says the electric flux is my enclosed charge over epsilon naught. So again, I don't know anything at the beginning about what the direction of the field is. Let's say that's going to come from our charge. So we will do the same steps here, right, where we say that the field vector is going to be parallel to dA. So that makes the dot product, right, of A dot B is A B cos theta. So when A and B are parallel, it becomes just A times B. Okay, so, and then we also are assuming that E is constant, right? If I put a Gaussian surface out here, and I draw it consistently, mine's a little bit warped, but there's no reason to think that the electric field over here is going to be any different from the electric field there if we are the same distance r away from the center. Okay, so if we make a surface that's equidistant from the center, then we can assume that the electric field is going to be constant there. So our integral is then the integral of electric field comes out. We just need to integrate our area vector along the surface of this outside Gaussian sphere, which again will give us the surface area of the sphere. Okay, and my enclosed charge now is negative Q over epsilon naught. Okay, so we're almost there now. We can solve for the electric field, divide by 4 pi r squared. Use up a little more room. So I get the electric field is negative Q over 4 pi epsilon naught r squared. Okay, so again, remember that this, just to relate to what we've done, right, K is 1 over 4 pi epsilon naught. So we can rewrite that, and again, it's the electric field as a function of radius, right, is negative KQ over r squared. Or we can leave it in terms of 4 pi epsilon naught if you like that better, right? So it's telling us that the electric field is negative, right? So it's pointing back toward the conducting shell. And I think that's it. Let's stop there. So by the way, this is why, we didn't mention this exactly, but this is why you can be in a car, in a metal car in a lightning storm, because the electric field will always be zero inside the conductor. Or the Faraday cage. Again, Google that in your spare time.